This is my floating bridge. It's built upon the principles of tensegrity, something which the legendary Buckminster Fuller came up with. I'll talk about that more later, but first, take a look at it. First, let's take a look at the design criteria. Does it span 30 centimeters? Yes, it does. Is it made of just cereal boxes, string, sticky tape and glue? Yes. Finally, will it hold 300-gram can of baked beans? Well, one small issue. I'm currently in Japan and we don't have any baked beans. So I'm going to make do with 2 cup noodles, which weigh just over 300 grams. So, let's see. Please work. And here we go. It holds 300 grams. That's all 3 criteria completed. So what is tensegrity and how does this bridge work? Well, to make it easier to explain, I'm just going to show you that these 2 are actually separate components, with each tube being its own tensegrity structure, and we're going to focus on this side. A structure that incorporates tensegrity has to have these 3 properties. It has to be built out of isolated parts, which are always under compression. We have 2 here, this bottom part and the top part. They're not connected by any rod or any solid structure. Second, these isolated components have to be connected only by either string or cable that's under constant tension. You can see we have 4 here. 1, 2 here under tension, and 2 more under these bars or rods or something. Third, the structure has to remain fairly rigid. It can't move around willy-nilly, otherwise that's not a structure, is it? So, how is this bridge, this half of the bridge, sort of floating? Well, this top part is sort of hanging from the bottom part. If we take a look closely at here, we'd see that this is below this rod. This rod here, the top rod, is below the bottom rod. And this string is under tension and it's been hung up. Also, the top part's center of gravity is this way compared to this string here. So, this top part wants to rotate like this. To stop that, we have a pair of strings here, which will provide an equal and opposite force to that turning motion, keeping it solid. So what are the pros and cons of a structure built out of tensegrity? Well, let's start with the good. Structures that incorporate tensegrity are very strong for their weight. They can hold a lot more because there are no redundant parts. Every string has its purpose. Also, any force applied to the structure will be evenly distributed across it, meaning that there's no one stress point, no one place which is under a lot of pressure. The negative. First, it is fairly complex and unorthodox, and we don't have well-established methods of analyzing a structure made out of using tensegrity, meaning it's very hard to design one. This is based on some Lego tensegrity sculptures that I found on Reddit, but there are one real-life bridge which looks totally different to this. Also, as the tensegrity structure gets more and more complicated and larger, strings and bars and components could just start running into each other, and that would not become a tensegrity structure. Now, I want to see how strong my bridge actually is, and I haven't tested this, so I don't know how this is going to go. First, my water bottle. It weighs 900 grams. Let's see. Don't tip, but please. If it stays on here, well, it's rolling away, but alright, crikey, how's this going to work? Well, my bridge now holds 900 grams, but I'm a bit concerned that these parts are now beginning to touch. It's probably because this cardboard box isn't as rigid as I hoped, and you might have noticed these flower pots. So that's to stop this bottom part from sliding outwards and just the whole structure rotating, because this isn't any held to the ground. So, well, it held 900 grams, so what's next? I was impressed with that last one. I was only building this in anticipation of 300 grams, but it held 3 times that weight. So now I'm going to step it up a notch with a 2 litre bottle of jasmine tea. 2 litres, right? Yes. This weighs 2 kilograms. That's 6 times more than it's supposed to hold. Let's see. Ah! It's not. No, it buckled. It buckled. It buckled somewhere. Something's gone wrong. Ah! It did not enjoy that. Don't know if you can see this well, but this part here just buckled, so 2 litres is out of the question. In conclusion, what do I think of this bridge? It's certainly not the best design. I mean, it puts a lot of strain on 8 locations. Well, equally, but there's still a lot of strain. An arch bridge perhaps would probably a lot better and stronger. However, I thought this would be a unique design and something that might catch your eye. And finally, thank you for watching.